Okay, so I have fixed my technology issue and I cleaned up the notes on this page a little bit so that it looks a little nicer if you're looking at notes after the fact. And now we are going to tackle our last problem from this chapter, which is problem 3.35. So this is 3000 problems number 3.35. And the problem says, a nut comes loose from a bolt on the bottom of an elevator as the elevator is moving up the shaft at 3 meters per second. So in this case, I would recommend that we draw a picture. Here's an elevator shaft, and here is an elevator, maybe being pulled by a rope or something. And then there's a little nut on the bottom, which comes loose, and it's going to fall down. But the shaft, the elevator itself, is moving upward at 3 meters per second. So we could say the initial velocity is 3 meters per second. Not only for the elevator, but everything in the elevator is moving at this speed, and everything on the elevator, including this nut, okay, this bolt. So if we want to see the initial path of the bolt, it has its own initial velocity, and it's going to go up a little bit, and then it's going to fall down. Okay. So it's important because it has an initial velocity that's upward. It does not just start from rest, but it's moving up. It goes up a little further. And now, while it's going up, the elevator is going up even more. Okay, so relative to the elevator, it just looks like it's falling down because the elevator is moving up at a constant rate, and this is sort of slowing down. If we would graph the motion of the elevator looks like that. And maybe if I use red for the bolt, it does this. So it's moving constant speed until it's released. Then it goes a little higher and follows this parabolic path downward. So the acceleration is going to be minus g because our problem is sort of turning on right here. This is where we might want to put the axis instead of over here. So it says the nut strikes the bottom of the shaft in 2 seconds. So from here to here is 2 seconds. We can just say t equals 2 seconds. And the first question is, how far from the bottom of the shaft was the elevator when the nut fell? So we want to know sort of x initial for the nut. And the x final is down here. So x final equals 0, and x initial equals question mark. Okay, so that's question A. And question B, we can kind of call that. Question B says, how far above the bottom was the nut 0.25 seconds after it fell? So somewhere right in here, probably up there, we want to know where that was. Okay, so for part B, we have some of the same initial information. The initial equals 3 meters per second, A equals minus G, but T equals 0.25 seconds. And we're looking for X final, and now the X final is not 0. Okay, that becomes our final. So let's do part A first. So for part A, when I look at this information and I see what's missing is V final, I really want to use my first equation. If we go back and look at our master equations, 2 and 3 both require V final, And so equation one that does not include the final. So we have delta x equals v initial t plus 1/2 at squared. And we check, do we know v initial? Yes. Do we know t? Yes. Do we know a? Yes. So we know all of that stuff. X final minus x initial equals v initial t plus, let's make this getting a little fancy here, minus g over 2. So I'm replacing the a with negative g. So that's going to move right on top of that fraction, and then we get a minus sign. And our x final is 0. So what we really have here now is an equation for minus x initial, or we can multiply both sides by minus 1 and get x initial equals minus v initial t plus g over 2 t squared. So again, I'm working with the symbols for practice, okay, rather than plugging numbers in prematurely. And we're going to get a minus 3 times 2 plus 4.9, that's 9.8 over 2 is 4.9 times t squared, which is 2 squared. So the x initial, let's see, do I need a calculator for that? That's 19.6 minus 6, so 13.6 meters. Okay, so that is the initial height, and that's part A. I would ask if there are any questions at this time, but since you're, viewing it from home without being live, then I won't ask. Then part B, I want to know how high it goes after this certain time, so I'm going to use the exact same equation. X final minus x initial equals v initial t minus g over 2 t squared, and x final is equal to x initial plus v initial t minus g over 2 t squared. And we know all of this information. I should put b's on everything, but I think we can probably keep it straight. So my x initial is what we solved for in the first part, 13.6 plus 3 times 0.25 minus 4.9 times 0.25 squared. And let's see what we get there. So I'm getting 14.04. So that's higher than the starting point, which is, I guess, one of the things I want us to see in this problem. I mean, I told you the graph looks like this, but if you don't draw the graph, you may not be expecting that the bolt actually keeps rising for a while before it comes back down. So because we pick only a quarter of a second after it's released, it hasn't had time to hit its highest point and start to fall down. So it's actually still on the way up. And we could verify that by finding the velocity. V final equals V initial plus AT, and that would be 3 minus 9.8 times 0.25. And that's 0.55 meters per second. Now, this last thing I did here was not technically part of the problem. I'm just illustrating the velocity after 0.25 seconds of the release is still positive. So it's still on the way up. All right, so that is the problem that we missed. And hopefully that will help you a little bit with the homework and the contest. All right, thanks, and apologies again for the technical difficulties in the lecture today.